Hello everyone, this is Mr. Win, and this video is over polynomial end behavior and even or odd functions. So polynomial functions are functions where every term has a variable and non-negative exponent. That includes constants because that is a variable to the 0th power. They may not have any other symbols, so no square root signs, absolute value signs, no fractions where x is in the bottom. Linear functions, quadratic functions, and even cubic functions are all part of the polynomial functions family. Polynomial functions are usually defined by their degree. Remember, the degree, or also called order, comes from the highest exponent of a variable. Also take notice of the sign of the leading coefficient. That's the constant multiplier for the term of the highest degree, as that is quite important for establishing end behavior. Note that the terms may not be listed in the usual descending order by degree. For example, what is the degree and leading coefficient for this problem? 3x squared plus 8 minus 4x to the 5th minus 9x to the 6th. We rearrange it and make sure the signs follow them. We can put the negative 9x to the 6th first. It's negative 9 because x is 6 highest power. Then the x to the 5th is next, but has a negative 4. And then x squared is third is positive 3. So positive 3x squared, and then positive 8 is last. Alright, so now we know that this is a 6th order or 6th degree polynomial. The leading coefficient is negative 9. Alright, so let's take a look at a few examples of some even degree polynomials. What do you notice about the end behavior? What do you notice about the leading coefficient? So here's the graph of x. F of x equals 5x squared. It is a 2nd degree polynomial, or y'all know as quadratic. The end behavior is the same. So remember, end behavior is the limit. So the limit of the graph of x as x goes far to the left, as x approaches negative infinity, will be positive infinity because it's going up on the left. If we keep going left, y keeps going up. Same for the right side. The limit of the graph of f of x as x approaches infinity as it goes right. So if we keep going right, y keeps going up. Alright, now you should do this for all of them, but I'm just be lazy. I'm going to say up and up. So left side is up, right side is up. Alright, also the leading coefficient is 5, but more importantly, it's positive. Here's the next one, x squared minus 3x plus 1. Again, this is quadratic or 2nd degree polynomial. The end behavior, left side's up, right side's up. End behavior is exactly the same, up and up. And the leading coefficient is positive 1 in this case, but it's positive. Over here is the 4th degree polynomial, x to the 4th plus 2x cubed minus 3x squared minus 5x plus 1. It could have a lot of things, right? It could just be a single thing or multiple things. It goes up and up. That is same end behavior. And leading coefficient, again, it's 1, but more importantly, it's positive. Then here, this is a 6th degree polynomial because it's 2x to the 6th minus 5x cubed. Left side goes up, right side goes up. So same. Leading coefficient is 2. Alright, so all even degree polynomials always have the same end behavior, no matter what. If the leading coefficient is positive, it's always going to be up and up. Now, what if the leading coefficient is negative? Well, the leading coefficient is actually a. We were doing the a, b, h, k transformation earlier. Remember, a controls the vertical stretch, vertical compress, and the reflection over x. So we're basically going to flip it over the x-axis. Instead of up and up, it's going to come down and down. So if the leading coefficient is negative, it will always go down and down. All right, let's look at a few examples of some odd degree polynomials. What do you notice about the end behavior, and what do you see about the lead coefficient? So the first one is f of x equals x minus 2. That is the 1st degree polynomial, or y'all might call it linear. If we go left, well, y goes down. If we go right, y goes up. So the end behavior is what we call opposite. So the limit of f of x as x goes to the left to negative infinity, y goes down to negative infinity. The limit of f of x as x approaches positive infinity as we go right is also positive infinity. So different. Alright, I'm be lazy and say down and up. So left is down, right is up. Alright, and the leading coefficient is 1 positive. Here's 3x to the 3rd minus 5x, 3rd degree polynomial, or you can call it a cubic. Notice the left side is down, right side's up. Opposite again. And this time the leading coefficient is 3, and again it's positive. Here 2x to the 5th minus 3x squared minus 1. That's a 5th degree polynomial. Left side y goes down, right side y goes up. Opposite again, down and up. Leading coefficient is positive. That's 2. Then 3x to the 7th minus x squared plus x, 7th degree polynomial. Left side's down, right side's up. So opposite, down and up. Leading coefficient is 3, positive. So here you should notice that all odd degree polynomials will always have opposite end behavior. If the leading coefficient is positive, it will always be down on the left, up on the right. Now if we multiply the negative 1, so a is negative, vertical stretch or vertical compress, depending on the value, but negative means flip or reflect across the x-axis. So we're going to flip this. Instead of down, up, it's going to be up, down. Alright, so if the leading coefficient is negative, it will always be up, down. Alright, so y'all try this problem. Below is the graph function. Does the function have an even or odd degree? And is the leading coefficient positive or negative? So I'll give you the quiz question now. Here's the answer. Odd degree because it's opposite, left's up, right's down. Now that's a negative coefficient because the normal end behavior got flipped, because usually it's down, up for odd, but now it's up, down. Alright, functions may have an even or odd property based on symmetry. Even symmetry means the function would be exactly the same if it was reflected over itself over the y-axis. Mathematically, that means f of x is equal to f of negative x. Odd symmetry means the function would be exactly the same if it reflected itself twice in a row, once over the y-axis and x-axis. That is considered the same thing as rotating the image 180 degrees. Mathematically, that means f of x is equal to negative f of negative x. If a function does not have even or odd symmetry, we say neither. And simple polynomials of one term will allow you to use the degree for even or odd, but if there are multiple terms, you must manually check using algebra. So let's take a look at these three functions. F of x equals x squared. So if we reflect over the y-axis, it will be the same, so it's even. So if I had to reflect this to the left side, it would be exactly the same, and this left side would go to the right side, would be right here. So it's the same graph, so it is even. We can do a quick check. Let's see if f of x equals f of negative x. So let's check f of 2 and f of negative 2. Well, f of 2, I go to 2 on the graph, it goes up to 4. So f of 2 goes 4. If I go f of negative 2, that gives me y value 4. It's a match. Algebraically, here's what we do. We know the original f of x. We're going to do f of negative x. So you did function notation. We're going to place every x in the original problem with a negative x. When you square negative, negative x times negative x, that's positive x squared. They are matching. Let's try this next one. F of x equals x squared plus 1. Here's the graph. If I reflect that, this turns to the left side, that's the same. And this left side goes to the right side, that's the same. So yes, it is even because it's matching after you reflect it over the y-axis, after you flip it sideways. Let's do a quick check. Let's try f of 1 this time and f of negative 1. If I go f of 1, I see the value is 2 right here. If I go to f of negative 1, the value is also 2. It's a match. Here's the algebraic check. You can plug in negative x for every x. So negative x all squared, negative x times negative is positive x squared, and the plus 1 didn't change. So it's the exact same equation. They match. Now, some kids say, oh, if it's x squared, even power, does that always mean it's even? The answer is no. Look at this one. Here's x plus 1 all squared. Here's the graph. If I reflect this over the y-axis, I flip it sideways, it's going to turn into this graph right here. Because this part goes to this side, and this part here will turn to this left part. So if we reflect over the y-axis, it will not be the same, so it's not even. So you have to be careful. Alright, here's the quick check. Let's look at f of 1 and compare it to f of negative 1. F of 1 for the original blue graph, if I go 1, it gives the value 4. If I go f of negative 1, it gives the y value of 0. So they're not the same. Here's the formal check. I actually just FOILed this out. So x plus 1 times x plus 1, if you distribute FOIL, you get this every common terms. If I plug in negative x for every x value, I'll get basically negative x plus 1 all squared. And if you FOIL that, you get negative x squared minus 2x plus 1. Those are not the same equation, so this is not even. Alright, let's take a look at some odd ones. Here's f of x equals x cubed. It's simple, polynomial. It should be odd. But let's look. If I rotate 180 degrees, it is the same. So notice, it goes down, up, and it goes to 0, 0. If I flip this, it's still down, up, because it's 0. Exact same graph. Alright, if you don't do like that, you could also reflect it over the x and y at the same time. So let me try my best to graph this. If I reflect it, let's reflect it over the x-axis first. It would look kind of like this. It's facing flip upside down, right? So this one to the down, and then this one to the up. Then I'd reflect this yellow one instead of reflecting over the x-axis, and I'd reflect over the y-axis. So this side would go to the right here, and this side would go to the left. It's the exact same graph. So it is odd. So you can do either one of those. I think it's easy if you just turn your paper upside down. Alright, let's do a quick check. F of x equals negative f of negative x. So let's check f of 1 for the original. So let me erase what I have right here. Alright, f of 1 in the original, 1 is right here. It goes to 1. F of 1 is 1. Now I'm going to check negative f of negative 1. So f of negative 1 gives me negative 1. And then I have to multiply that by negative 1. So negative 1 is positive 1. So 1 equals 1. That's the match. Alright, here's the formal algebra. The original is x cubed. I'm going to plug in negative x for every x in the original. And then once I finish that, I'm going to multiply the whole equation by negative on the outside. So negative x cubed, negative times negative times negative is still negative, and x times x is x cubed. Then a negative x cubed is positive x cubed. They're matching, they're the same. Here's the next one. X cubed plus 1. Alright, first let's try rotating it. Is it the same? Notice that this graph is going down, up, and it's going through, I guess, the y-intercept of 2. If I flip this, is it the same graph? The y-intercept was positive 2, and now the y-intercept is negative 2, so it is not the same graph. It is not the same. So, if rotate 180 not the same, it's not odd. We can try the reflection trick to draw the reflection. So I'm going to try reflecting it over x first. So if this went down here, it looks something like this. Alright, so that is reflected over x. Then I need to reflect it over y. So I'll use a purple line. If I reflect this over the y-axis, this will go over here. How do I make this? Alright, it'll look like this. Alright, that would be the graph. Ew, that last part looked bad. Okay, so notice this purple line is not the same as the green line. Alright, so let's do a quick check. I want to leave a purple line there. I'll show you why in a second. Let's check f of 1 and negative f of negative 1 for the original graph. F of 1 goes to 2. F of negative 1 is 0. So negative 0 of 0 is still 0, not a match. Here's the form algebra. Here's the original. I'm plugging negative x for every x first. Then once I finish the whole thing, I'm going to multiply the whole equation by negative 1. So negative x cubed, I know that still is negative x cubed. Plus 1, I distribute this. This will be positive x squared minus 1. Notice this is actually the purple line I drew, right? It's the cubic that was transformed down 1. So these are not the same. And here's the last one right here. X plus 1 all cubed. Here's the graph. If I turn this upside down, will it match? It's all on the left side right now. If I graph this, I flip it, it's now on the right side, so it's definitely not the same. Alright, so the flipping trick upside down did not work. If I try reflecting it twice, let's see what happens. I'll flip it downwards first, so this top will go to the bottom. Go like this. So that's the first part. Then I'm going to reflect that over the y-axis, going sideways. So this will come over here like that. And then this will go like this. Alright, so there's the picture. But again, it's not the same as the blue one. The quick check fails. So let me try f of 1 and negative f of negative 1. Now f of 1 isn't in this graph, so what I did is actually just plugged in 1 to the equation. 1 plus 1 is 2, 2 cubed is 8. Then when I went f of negative 1, that was 0, and then negative 0 is 0, so those don't match. Here's the form algebra check. I plugged in negative x for every x. Then once I did that, I multiplied the whole equation by negative 1. Notice that this final equation does not match the original equation. It's close, but the second thing changed signs from a positive to negative, and the last thing changed signs from positive to negative. Alright, so using only the graph to determine which function is even, odd, or neither. G of x is down here. If I flip it sideways, that's going to match. That's even. If I rotate it upside down, it'll go up here, so it's not odd, and then since they're even, it can't be neither. H of x is this. If I flip it sideways, it's not going to match because this top will go to this part right here. If I flip it sideways and then flip it downwards, it will match. So this is going to be odd, and then f of x, if I turn it sideways, it'll look like this. If I rotate it upside down, it's still not going to match, so that's neither. Sometimes you have to do it without a graph, determine whether this function is even, odd, or neither. So we have to find both f of negative x and negative f of negative x to see if they match. Here's the first part. I plug in negative x for every x. Then I calculate, you get a negative x all cubed stays negative. A negative x squared times positive, but don't forget this negative sign here. That just is negative x. I multiplied, I got all this once I did so this is not matched to the original, so it is not even. Let's try, see if it's odd or not. I plug negative x for every x, and then I'm going to multiply the whole thing by negative 1 once I'm done. So like earlier, this is negative x cubed. Negative x squared is positive, but don't forget the negative in front of it. That's negative x, that's plus 2. I fix this, I distribute, I get this. Does this match the original? It does not. The sign for the second thing is wrong, the sign for the last thing is wrong. So since it's neither, it's well, it's not odd and it's not even, so it's going to be neither. And that's it. If you have any questions, make sure you ask. See you soon. Thanks for watching. Bye. By the way, one last trick, we already found f of negative x right here. I just had to use this and multiply all by -1 to get this last answer.